Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, 9.1, Angular Velocity. Part of the chapter 9, Linear and Angular Velocities of a Rigid Body. We first perform some insightful calculations on rotation matrices and then explain their meaning as the body angular velocity in inertial and body frame, respectively. Time derivative of rotation matrices. Recall the set of skew-symmetric matrices SO3 and the operation from R3 to SO3. In addition, given a matrix R of t with entries Rij of t, the derivative of R of t with respect to time is a matrix R dot of t with entries R dot ij of t. Lemma 10.1. The time derivative of a rotation matrix. Given a time-dependent rotation matrix R of t, i.e. a curve of rotations or a trajectory in the set of rotation matrices, has a different rotation matrix for each value of time, right? There exist time-dependent vectors omega left in R3 and omega right in R3, such that R dot is equal to omega left with the hat. Remember, the hat operator gave us the skew-symmetric matrix constructed from a vector. So omega left hat R equals R omega right hat. Equivalently, we can write omega hat left equal to R dot R transpose and omega hat right equals R transpose R dot. We reason along the following lines. To begin, we consider the equality R transpose equals the identity matrix. That's true because a rotation matrix has an inverse that is just its transpose, right? So R transpose is R inverse, and an inverse of a matrix multiplying a matrix is going to give the identity matrix by definition. And compute its time derivative, dropping the time argument for simplicity. So we get R dot R transpose plus R transpose dot equals a 3x3 zero matrix. If we define S of t to be R dot R transpose, then the previous equation implies that S plus S transpose equals 0, the zero matrix. And in turn, that S of t is in the set SO3 for all times t. Therefore, there must exist a time-dependent vector omega left in R3 satisfying omega left turned into a skew-symmetric matrix equal to S equals R dot R transpose. Post-multiplying both sides of the latter equation by R and using the fact that R transpose is the identity matrix, we obtain that R dot is equal to omega left hat R. To obtain the alternative result with omega right, we perform the same calculations starting from the equality R transpose R equals the identity matrix instead of R transpose, which both are true, of course. Okay, the derivative of a rotation matrix with respect to time is related to the angular velocity of a rigid body, or equivalently of a frame fixed with the body. The previous lemma tells us that differentiating a rotation matrix is equivalent to multiplication by a skew-symmetric matrix. Notice, however, that there are two ways of computing the derivative. Let us immediately clarify the meaning of the left angular velocity omega left. Lemma 10.2, relationship between the classic angular velocity and the time derivative of a rotation matrix. So we're going to relate the time derivative of a rotation matrix that we just derived to what you're familiar with from your dynamics class regarding the angular velocity of a body. Consider a rigid body possessing a point O fixed in time and rotating about an axis n with a scalar angular speed theta dot. Take two reference frames, sigma 0 and sigma 1, coincident at time equals 0, and with origin fixed at O, both of them. Assume sigma 0 is fixed in space and sigma 1 is fixed with the body. Let R10 represent sigma 1 with respect to sigma 0 in our usual notation, so that R10 dot is equal to this skew symmetric matrix times R10, which we derived earlier for any rotation matrix. Then omega left is theta dot n0, which is to say the n-axis expressed in the 0 reference frame. Thus, we see that omega left is a vector pointing along the axis of rotation and with length equal to the angular speed. That is, it is the angular velocity of the rigid body. Proof. We reason along the following lines. To begin, take a point P attached to frame sigma 1 and note that the time derivative of P1 is 0. That is to say, it's fixed in the body fixed frame by construction. Of course it is. It's fixed on the body. It's fixed in that frame, so it's not going to change position relative to the moving frame. From the classic notion of angular velocity as illustrated in figure 9.2, which is right here, we know that if you want to find the velocity of a point, we take the time derivative of its position. If its position vector is p0 in the 0 reference frame, we would take its time derivative to find v0, its velocity in the 0 reference frame. And we know that it is the angular velocity, scalar, times the axis, so the vector angular velocity, cross p0. Next, write p0 equals r10 p1, which is to say just a basis transformation or a reference frame transformation, and differentiate with respect to time to obtain, so now we're taking the time derivative of p0, so the position of that point in reference frame 0, no longer is that going to be a fixed point, right? So r10 dot p1 omega left hat r10 p1 equals omega left cross p0 of t, where we've used the property that for a vector omega and its skew symmetric matrix omega hat, we have that the cross product with a vector v satisfies omega cross v equals omega hat v, so multiplication instead of cross product. So what we've done in this last step, we've actually done two things. The first thing we've done is say r10 p1 is just p0, right? It is p1 rotated into the 0 reference frame. And so p0 is that point. And omega left hat times this p0 is what we have before we make this last statement that we make. And what we've done there is we've just said, oh, well, we have a skew symmetric matrix times v, or times p0 in this case, and we can rewrite that as the cross product. The reason we're doing that is we want to make it look like this classical definition of the velocity. Okay, the classic definition of the velocity where we have the angular velocity crossed with the position. So, equating the last two formulas, we obtain the fact that omega left of t is just equal to theta dot, which is to say the speed in the direction n0, in the direction of the axis of rotation, and noting that p0 is arbitrary, we have established the desired result, which is to say that omega left is the angular velocity, even in the classic sense. Okay, angular velocity in inertial and body frames. Now that we have more properly explained the meaning of the left angular velocity, omega left, we are ready to give it a more explanatory name and symbol. In the previous example, r10 dot equals omega left hat r10 clearly implies the following two facts. Omega left is the angular velocity of sigma 1 with respect to sigma 0, and omega left is expressed in the frame sigma 0. Okay? As a consequence of these two facts, we introduce the following notion: angular velocity in an inertial reference frame. Given a rotating frame, sigma 1, with fixed origin, its angular velocity with respect to a fixed inertial reference frame, sigma 0, expressed in sigma 0, is sigma 0, 1, 0 hat equals r10 dot r10 transpose. Okay, so let's read out this notation. So we have omega 0, 1, which means the angular velocity of the 1 reference frame with respect to the 0 reference frame expressed in the 0 reference frame. That's the superscript, expressed in the 0 reference frame. Next, we need to properly explain the meaning of the right angular velocity, omega right. First, from section 7.4, the appendix on skew-symmetric matrices, a useful property of the skew-symmetric operator hat is that RU hat R transpose is equal to quantity RU hat. Or, equivalently, you could write that RU hat R is equal to RU hat. Starting from angular velocity in the inertial frame, R10 dot is equal to R01 expressed in the 0 frame, hat R10. We define the angular velocity in the body frame, omega 0, 1, 1, so in the 1 reference frame, by requiring it to satisfy the standard change of reference frame relation that omega 0, 1, 0 is equal to R10 omega 0, 1, 1. Again, subscript, superscript, denoting the reference frames, is matching. Finally, we put it all together and compute, dropping the time argument for simplicity. R10 dot is equal to R10 omega 0, 1, 1 hat R10, which is equal to R10 omega 0, 1, 1 hat R10 transpose R10, and these two are inverses of each other, right? R10 transpose R10 become the identity matrix, and you're left with just the left two terms. This derivation implies that omega 0, 1, 1, this guy here, is equal to omega right, and the following definition. Definition 10.4, angular velocity in the body frame. Given a rotating frame, sigma 1, with fixed origin, its angular velocity with respect to a fixed inertial frame, sigma 0, expressed in sigma 1, is omega 0, 1, 1 hat equal to R10 transpose, we have to have that transpose in there, R10 dot. Finally, it is interesting to consider a point P attached to the body frame sigma 1 like we did previously, so that P1 dot is equal to 0. So in the body fixed reference frame, that point isn't moving because it's fixed relative to that point. It is, say, a point on the rigid body. We can compute that the time derivative of P0, so the same point but expressed in the 0 reference frame in which it is not fixed, we have sigma 0, 1, 0 cross P0, okay? Sort of the traditional expression for the velocity of a point using the angular velocity and a position vector. Okay, that's all I've got for this lecture. I'll see you in the next lecture. Take care.